the state of California. Before jumping into the seismic hazard definition, I need to mention that our goal is here to design to be hazard consistent, meaning to be consistent with expected hazard in each specific site. And for this sake here, we used 4 different locations in the state of California. In the state of California, these locations are located in 2 different categories: high seismicity, like San Francisco Bay Area and Los Angeles, and low and moderate seismicity, like San Luis Obispo and also Sacramento. And you can see the density of transportation network in the state of California. So these are the locations that we need to make sure we could provide a solution for temporary relief.
Oh, I'm not sharing the screen, sorry.
I'm sharing the screen.
Sorry.
Let me just share this. Okay right now? Should be good. Please check it.
Yes.
Is it the ground? Yeah. Is it full screen or with the notes?
Yeah, it's no. You have for the screen. Mm-hmm.
So you check it. Make sure it's okay.
It's okay now.
Okay, good. So we're trying to find a hazard consistent design for such location, and we're using 4 different locations. 2 high seismicity and 2 low to moderate seismicity. And you can see the density of transportation network across the state of California here. For high seismicity location, as I mentioned, we are looking for Los Angeles and San Francisco here. These locations are considered as near fault because they are located within the 15-kilometer from the fault. And for the location of San Francisco, Hayward Fault is the most contributing fault according to seismic deaggregation. And Elysian Park is the one with the most contribution for Los Angeles. And for low to moderate seismicity, we are looking at San Luis Obispo and Sacramento. For both of these locations, we are seeing San Andreas as the most contributing fault, and these are considered as far fault from according to the definition of ASTE7. So in order to design this structure, primarily seismic design, we need a design spectrum. And the way that Caltrans do it is using the UHS, or Uniform Hazard Spectrum, that comes from probabilistic seismic analysis from hazard curve and then transferred into these spectrum. So this is going to be our target spectrum that we want to use for designing. And per recommendation of Caltrans, in the first slide, we saw that they use 100-year return period for designing this structure. So obviously we are using the 100-year as well. And we are seeing 1 level above and 1 level below. The level above is going to be 200-year, which is return period, which is correspond to 2.5% probability of exceedance within the 5 years, expected life service of the bridge. And also for the level below, we are seeing 50-year return period, which is corresponding to HL1, we want to call it from now, corresponding to 10% probability of exceedance within the 5 years of our life service. And we use the USGS Uniform Hazard tool to derive these UHS curves based on the location. And the assumption based on the request of the Caltrans was for all of these locations, a site class D with a shear wave velocity of 259. And for the sake of this research, because we have 2 locations that are located within the fault, we also check the effect of basing and also the near fault using the recommendation of Bozorgina 2014 and Caltrans SDC. Only location that could be affected by the Bayesian effect was the Los Angeles, which was not in our case. And also we checked the near fault effect using Caltrans method, which is the amplification method. That can you see the figure on the below here? It's a multiplier that is equal to 1 from 0 to 0.5 seconds and linearly increased to 1.2 on the period of 1 second and constant afterward. And it's going to only affect the long period acceleration of our spectrum. So by doing so, we derive such spectrum here, as you can see, for 4 different locations: San Francisco, Los Angeles, San Luis, and Sacramento, with 3 different hazard level HL1 to HL3. Next step, in order to be able to use ground motion for nonlinear time history analysis, we need to first select the ground motion, then scale them and use them for our analysis. In this context, we are following the standard approaches for ground motion selection within the literature, but with a few adjustments. In the first step, we define the magnitude, the rupture distance, and shear wave velocity range in order to be used for each specific location to be able to search into NGA-WES2 database for our ground motion selection. This data comes from the seismic aggregation, which provides us information about the most contributing and governing seismic event, about the magnitude and distance for each specific location and hazard level. And the next step, when we have initial list of the ground motions, we need to consider combining 2 of horizontal components, because we know that there's 2 horizontal components for each ground motion. And if we want to scale and check these spectral acceleration within our target spectrum or our UHS, which is defined on the previous slide, we need to combine these 2 components together. And the way we do and the way Caltrans suggests to do is using the geometric mean for our case. So by calculating the geometric mean, we have a component that is coming from both horizontal components of each ground motion source. On the next step, the scale factor is calculated, which is using the formula as you can see on the screen. And this scale factor is calculated within a period range of interest, which is for our case is 0.5 T1 to 1.5 T1 according to AASHTO 2020. And the T1 is the fundamental period of the structure. By calculating the scale factor, we are able to calculate the MSE, which is the mean squared error, that shows us how much difference, how much error does it exist between our target spectrum and our ground motions. And then by sorting these, for example, initial list of ground motions, based on the MSE that is calculated on the last step, we are able to rank all of these ground motion and use the first 31 that fits within the search criteria for the scale factor between 0.3 to 3. So this kind of gives us the 30 final ground motion for each hazard level and each specific location. And the next step, we check that there is a sufficient number of impulsive ground motion by the work which is done by Hayden et al. In 2014 in our ground motion suits. And as per request of Caltrans CC, we rotated twice these ground motions to have all of the components to be to have a possible orientation for different bridge orientation, creating a total 19 ground motion for each hazard level for each location. And you can see a sample of this scaling. As you can see, the scale range is shown here, and also you can see the target spectrum with the black, and also the median of selected ground motion, which is the top 31, and also plus and minus standard deviation. So since we twice rotate these two, it's going to be 0 and 90 degrees, just the component will be swapped, and also one separate 45-degree component here. Okay, let's talk about the bridge itself. So there are a variety of the temporary bridges used by the Department of Transportation, but the one that we are here using, and is per suggestion of the Caltrans, is called ACRO. ACRO is the name of the manufacturer, and these are prefabricated steel modular bridges, as you can see on the bottom part of the screen here. That is really easy to erect and can be simply assembled on the site and then transferred or pushed on the top of the substructure. And this is actually the latest constructed ACRO bridge in the state of California. It's located on California US 101 road, and it's called Dr. Fine Bridge, which was the name of the previous bridge that is demolished here. You can see columns here, and it's taken from Caltrans District 1X, or previously Twitter Bridge. And you can see the superstructure actual here. I'm going to talk about more about the hinge later. And this is the total shape. And it's a multi-span with irregular substructure, but the one that we use in this scope of our structure is two-span continuous deck and with a lightweight superstructure. So the lightweight superstructure, I need to define a parameter here, which is called ALR, or axial load ratio. For the typical ordinary bridges, we are talking about the ratio of axial load to axial resistance of the column, about 10 to 15%. But in our case, since it's temporary bridge and it has a lightweight superstructure, we are talking about 5% and below. And this lightweight gonna affect the mass of our structure, is gonna affect the modal behavior, seismic behavior, and also the design of our solid structure. And for the geometry and initial properties, we use the one that is get from manufacturer, and also the deck itself assumed to remain linear during our analysis, and the nonlinearity is concentrated in our substructure or our column. For our substructure, we are talking about a two-column band, which are CIP, or cast in place, with reinforced concrete columns, and we use the circular cross-section with fixed pin boundary condition. So in order to design the bridges, we already talked about the existing hazards that we have, and also the size, the bridge itself. Let's talk about the design. The main goal of the design here is to stay within site-specific and hazard-consistent bridge design, which is specifically for each location. And we are using it, we are trying to achieve it using columns displacement ductility method provided by Caltrans, which is calculating the mu D, as you can see. For this design purpose, we need to generate two different models, one linear and one nonlinear. For the linear model, we have done a preliminary design by hand, then transferred it into the CSI bridge to design the linear model and conduct elastic dynamic analysis according to Caltrans preferences to get delta D, or displacement demand. And also, it's good to mention that the acro deck is going to be linear again. All of the elements are linear, and also the pin connection, which you can see here, is a type of a special connection that allow rotation freely in transverse direction and to some extent along the longitudinal direction. And the columns base are also fixed. So this is going to give us the delta D, or elastic displacement. We have done dynamic analysis and extract the values using two components in transverse and longitudinal direction. For nonlinear model, we generated nonlinear model in OpenSeas using nonlinear material definition. For the concrete, they have used concrete O2 material with two separate definitions. One is for confined concrete using Mander's model in 1994, and the other one is unconfined. For the rebar, we use the hysteretic material to be able to capture asymmetric and buckling behavior of the rebar. In this case, we used the Zhang's model in 2014 and calibrate the model and the damage parameters based on the experimental test, which is going to be shown on the next slide. And then we incorporate these materials into our fiber section to have a nonlinear section. For the element itself, as per request of the Caltrans, we use concentrated plasticity. So for concentrated plasticity, typically there is a hinge at the bottom or even top of the column, or both. And the remaining length of the element could be linear. But in our case, we use the remaining part again with the fiber definition to make sure how much plastic hinge could be spread along the length of the column. And also the plastic hinge itself was defined based on the equation provided by Caltrans. And also we check the value to make sure that the classification stays within the calculated value. And the element itself is nonlinear beam column. So using this nonlinear model, we extract the yield displacement. You can see some of the results here. For different designs here, we have the elastic displacement and we have the yield displacement. And the ratio is easily just calculated by having these values together. So for our case, for this type of the bridges, which is not essential bridges, according to the definition of the Caltrans, the value of the mu D should be less than equal or true, in which for our cases, there are less than equal to confirming that our design is accurate according to what Caltrans wants from us. And the final result of the design is provided here. And as you can see, in the majority of locations, hazard level, except the San Francisco, you see that the longitudinal reinforcement is less than 1%. So this 1% ratio is a prescribed value by the codes like AASHTO and also ACI that is going to prevent problem that might cause by shrink, and also because the value is less than 1%, we are some kind of trying to show that we are relaxing the prescribed value by the code. And this is going to also affect on transverse direction as well. So we are looking at 0.5% as a minimum reinforcement, but we are seeing 0.3% as a calculated reinforcement for the transverse direction. And for the majority of the location, we are seeing 0.8, 0.4, 0.7, which is less than 1%. So the design procedure itself is an iterative procedure. We need to make sure that the value that is extracted from nonlinear model is accurate, or simply our nonlinear model is working properly. So before finalizing the design, we have to make sure that these values are correct. So in order to do so, we use some experiments in the literature to validate our numerical model. And as you can see here, the one that we use goes for Lemon and Henry in around year 2000. And you can see the results here. The main reason that we use this experimental test to validate how our model is that when we use the hysteretic material to define the rebars, there are some damage parameters that control the pinching in cycle and out of cycle degradation. And we use these experiments to calibrate these values into our model to make sure we are able to capture the correct value. And we need to find a way to classify the damage that we see in a bridge. And the way we do is by using a system called damage state. The one that you see here is a six-step damage state that is widely used by Caltrans. It was generated in 2010 by Usuki and Saidi here at UNR. And if you want to categorize it, it's going through three main categories. The DS1 and DS2 is talking more about the minor repairable damage. And the DS3 and 4 is more extensive damage that we saw. And as we go toward the DS5 and DS6, it's more toward the near collapse experiences that the structure can be told. And also, I need to mention that these are qualitative damage states. So since we are working on a numerical model, we need to have a way to quantify these values. These are based on visual inspection, and we need to make a criterion, as you can see on the second column, to use in our model. This was done through a meticulous stress analysis in our work. As you can see, this is, for example, a cross-section of one of our bridges. And as we increase the drift going toward the right, we see that the hashed areas are showing the tension cracks and hatched rebar showing the rebar yielding. So as we increase the drift here, the first fibers in cover start to crack in tension, then the crack spreads toward the neutral axis, then the yielding is going to start on the top and the bottom rebar with the cracks in the core, and it's going to spread along all the cross section. And based on this principle and the criterion, we were able to measure different damages set in our model. As you can see on the right, we have the same on the pushover curves for San Francisco, Los Angeles, San Luis, and Sacramento for DS1 to DS6. So let's talk about the bridge response statistics. So here we have some box chart. This is the first set of results that we're going to discuss about that. The box charts are showing maximum, minimum, median, plus and minus standard deviation here. And the first insight that we saw here is that the median of the response is always equal or below DS2. And the DS2 is corresponding to what we call a minor and repairable damage. And we have a response that is consistent with the design that we have already adopted and is hazard consistent design. And we have a consistency even when we go below 1% in our model, which is for two locations, hazard level HL1 and 2 in LA, and HL1 to 3 for San Luis and Sacramento. So we are trying to show that by relaxing the codes criteria, we could achieve a safe, hazard consistent design that withstand within the range DS1 and DS2, which is the repairable damage that we want for our models. And also, the point to mention here is that you see a jump here for HL3 here, which is not the case for all other locations. And this jump is primarily due to the reason that we have a high polarization in some of our ground motions selection for this specific site. And that explains why we saw such a jump from maximum value in San Francisco HL3. So we use these values for drift statistics and incorporate it into the principle of probabilistic seismic demand model for PSDM, and do a regression between our engineering demand parameter, which is our drift, and also the corresponding spectral acceleration for the fundamental period of the bridge within the ground motions to have equation between these two. And using the principle of cumulative density function, we are able to generate fragility dots, which shows the probability of exceedance for each of these damage states according to the hazard, according to the damage state that we define earlier. And by fitting these dots together, we are able to generate the fragility curves, which show a continuous probability of exceedance for each specific damage state for each location. And by using the same procedure here, we were able to generate fragility curves for all different locations. In this figure, from left to right, you can see start from San Francisco and Los Angeles to more seismically active areas going to San Luis and Sacramento. And when we go down, it's increasing the hazard level from HL1, which is corresponding to 50 years return period, going to HL3. And this dotted line here is the corresponding design spectral acceleration on the fundamental period of the bridge. And the most important takeout from this figure is that, except for this specific location, as we discussed on the previous slide, from our location, we see zero probability of exceeding DS3, which means that we do not expect to see extensive damage in our bridge. It's going to be maintained within the zone of repairable damage. And even for this one here, HL3, we see a low probability of exceedance. And also we need to consider this in mind that we are relaxing the code criteria. We are showing that using lower than 1% reinforcement could yield to this hazard consistent design. So the repairable damage across all locations and hazard levels are seen here. And using these fragilities here, and if we combine these fragilities all together to generate a general fragility curve, and by integrating these fragilities with that current existing hazard in our model, you're able to calculate the risk. And we have the probability of exceedance for all hazard level locations for each damage states. And by combining these together, we are calculating the risk. And also, it's important to mention that here, we are using 2 extra lifespan here. Primarily, we were talking about 5 years, but now we are checking 10 years and 15 years to see if the bridge would stand more than the expected life service, what will happen. And the thing that we see here is the fair consistency across all locations for the same damage state. And as you can see here, we are seeing, for example, for the DS1 between 2 high seismicity areas, which are we are more interested in, we see 855 and 837, which are fairly close to each other, and also 5.28 and 6.34 for low seismicity areas. And for example, in all of the risk analysis is showing that the risk is only concentrated within the DS1 and DS2, and the only location that has the risk of exceeding DS3 is San Francisco, but you can see that it's fairly low, below 3% if we use the bridge for 50 years. But if you want to stick with the 5-year assumption that we have from the first place, it's going to be less than 1%. So this was the first step. The second step is what happens if a beyond design earthquake hits our temporary bridge? What will happen? So what is a beyond design earthquake? So we were talking about 100-year return period, 200-year return period, but for the ordinary bridges, we are talking about 975 years or even 500 years, depends on the case. So in this step, we are trying to check that if we design a bridge based on 100-year or 200-year, what happens if 500-year earthquake hit the bridge? And the first one is again the same. You can see the drift statistics here. As you can see for 500-year and 975, we cannot see such consistency as before, as the median is just varying within DS3 or DS2, or even in 1000-year, we are seeing DS5 and DS6 even for the maximum values, showing that these bridges could go under extreme damage under 975 and 500 years here. And we don't see such consistency. That's an important point to mention for the risk analysis for the next step. Using the drift data from previous slide, again, we are trying to generate the same procedure, generating the fragility curve again. The HL2 design and HL3 design was studied in the first stage of this presentation. And again, the fragility curves are provided for 500-year and also 975 or easily 1000-year. And you can see here, for HL2 here, we are seeing above 90% probability of exceedance for DS3 and about around 40%, which is for HL2 design for San Francisco for DS4, which is the high value. And also here for 975, we see almost 100% exceeding DS3 and above 90% exceeding DS4 for HL2. But the important point to make is that we are again checking the values for different locations, that majority of them are below 1%, which is the code described value. So by having all of these results together, we can explicitly compare the design that we have. So in our case, the performance that we want to just check, if we extend the 15-year lifespan of the bridge, what will happen to the risk? So as you can see here, in terms of the DS3, which is the starting point of getting more extensive damage, we see that by increasing lifespan of the bridge from 5 years to 15 years, we see a minor increase, and it's fairly consistent within all locations. And even if for HL3 design, the values are again lower. So, and also if we want to exceed the DS3, the risk is fairly low, it's below 2%. And the most important takeout here is that whether if we want to stick with the idea, with the assumption that the Caltrans use right now to use 100-year, a 5-year lifespan is going to remain fairly low risk to design for 100-year for our bridges. And if the bridge is overused for example, 15 years, the value of the risk remains fairly low. For example, for DS3, it's going to be less than 4%. For HL3 design, it's going to be less than 3.75. And if you want to extend the value, goes to the higher level of damage, for example, DS4, again, more extensive, or even near collapse, you see that the values are fairly low, showcasing that having the design spectrum responding to the 100-year is a reasonable approach that Caltrans suggests to use. Okay, so let's conclude. So for our the main objective in our discussion was to provide a basis for developing recommendation to achieve an economical and based on the performance and current existing hazard that we have in our sites. Sites are across different locations in the state of California, from high seismicity to low seismicity. And the first takeout is showing that this hazard consistent approach that we use in our research is gonna provide us a satisfactory performance for our bridges. Also, we just relaxing the minimum requirement by the code like AASHTO. And it's going to be expected the 5 years to be the good estimation for the bridge, and 100 years is a good estimation for the hazard design. And also for developing, there is a need also for developing minimum design requirements. As I briefly mentioned that one, the minimum design requirement within the codes is based on the concrete creep. And also the thing is that this is based on the actual ratio ALR of the columns that are for full weight structure. For the lightweight structure, like the one that we have here, which also has the short lifespan of 5 years, it needs to be revised and also incorporated in the literature that the minimum designs could be relaxed and could be reconsidered again. And the last takeout is going to be, it's been demonstrated that the adequacy of this 100-year return period is an accurate approach showing the low risk of exceeding beyond repairable damages in different locations across the state of California. So for the future work of this research, we are primarily focusing on do a performance evaluation of the temporary bridges that we adopt using a normal weight superstructure, because this is another option that DOTs like Caltrans use. And we are trying to do the evaluation and compare it with the result that with the temporary structure with the lightweight that we have right now. And also, we need to check the impact of multi-span configuration, because here in this scope, we are only checking 2-span bridges. And for the extension of the work, we are looking at multi-span configuration, since the literature insists that if we increase the spans from 3 and above, it's going to affect the dynamic behaviors of the structure. And since it has been zero research on this topic, it's good to dig more and just scratch more the surface. For the last part, right now, actually, we are working on developing a new damage set definition. As I mentioned earlier, the one that we use in our work is a 6-set damage set DS1 to DS6, which is primarily defined for the bridges. But here we're trying to develop a more simply to use damage set, for example, something near AC41 suggests a triple level to be used for temporary bridges especially, and incorporate the fact that these bridges are lightweighted and they could be designed without the criteria prescribed by the code. So the general idea here for the future road of this research is to do the foundation for developing a unified recommendation for different DOTs, especially the one that is our sponsor, Caltrans. So they were able to use for a hazard consistent design that is cost effective for such bridges that could be used primarily as a solution for their disruption in transportation networks. As a part of this research, these are the outcomes that we had until this moment. So we had a manuscript accepted for a conference in Arizona Structural Congress 2025. And also we have a paper under review on the Journal of Bridge Engineering ACE. And also the report from Caltrans is on the final stage right now. It's waiting for becoming online and approved for final approval. Thank you very much for your attention. I will continue.
Thank you so much, Marty, for that insightful presentation. We will now open the floor for questions. Please raise your hand. We will invite you to speak.
Thank you so much for the presentation. Comparing all the seminars that we had last semester, this one had to be like the most well put together presentation I've ever seen. So thank you so much for that. Wow. So I guess a good question would be, are there any other DOTs that are coming up to you guys for this type of research besides Caltrans? Or is it mainly just because they're sponsoring it?
Or for the sake of this research, since the Caltrans is a sponsor for this research, we are primarily contacting them because they are paying for the research actually. But the idea is could be used in each state, every location in the US or even out of the US. But since the sponsor is Caltrans, this project is specially designed and done for the Caltrans. That's why we're always talking about California, location in California. So in other locations could be a little bit more different, but the idea remains the same.
Thank you so much.
I'm going to preface this by saying I'm not a concrete person. Okay. So you have standards like minimum reinforcement ratio for 1%, being 1%, and some other. I'm curious about like whether you considered or how you considered like minimums to achieve ductility.
Mhm.
And if you do things like drop the longitudinal reinforcement ratio, drop the transverse reinforcement ratio, like even, you might predict okay performance, but how are you considering what you need to guarantee ductility, and can the models predict that?
So the ductility that is need to be provided, that's such a good question, thank you very much, is actually achieved through the design procedure that we adopt from Caltrans SDC. So let me just go back to the design slide here. So the ductility that we want to achieve here is actually the ratio between the displacement that we have to the yield displacement that we show here. So by checking with the displacement criteria that STC provide us, we are making sure that we can see the expected ductility for a 5-year lifespan for such a bridges that could be achieved less than 2. We don't want such a value to be really high, above 2.5 here, which could be used for ordinary bridges. And for the sake of this research, since they are temporary bridges, we are not expecting to see super ductile behavior such as the ordinary bridges that provide essential connection. That's why we are checking a ratio below 2% that can guarantee the expected corresponding to the temporary bridge that we use. Yeah.
Because the others have been super nice. If that's SDC and your columns are single curvature because you print at the top.
Yeah.
So minimum displacement ductility capacity is 3, and the maximum displacement demand is 5, not 2. So the displacement demand should be less than 5, which is obviously on the slides and very close to you. And the capacity must be more than 3. I haven't seen any slide. We had one pushover curve state on it, but in a report the displacement capacity.
I could do so, but here we're just reporting the ratio here. But since it's not essential bridge, according to Caltrans definition, we were able to relax these values a little bit. That's why you see such difference. And it's primarily because of the contact with Caltrans in different part of the project.
Yes, that one totally makes sense. The question I want to ask you is your hinges. The hinge that you're showing there is bolted both sides to the cavity and the column, or it's
This one here?
Yes. Or it's allowed to move in the transverse direction.
So the transverse direction movement is restrained.
Okay.
It just allows rotation in the transverse freely and to some extent along the longitudinal.
Okay, so it can move in both directions except the end point.
By move, you mean rotating?
No, just move in this place.
No, movement is fixed, just rotation is allowed.
Okay, so that is a continuous beam sitting on top of cavity essentially. Okay, the question that then comes is, yes, you have the low axial load because your superstructure is very lightweighted. Then your behavior is very close to being real.
Exactly.
All of which is good. But the question is, the way that you are modeling it, did you include the pounding effect at the bottom? Perfect.
No, I need to explain it, just continue.
Okay. Yeah, just checking if everything went into the system.
Okay, so for the pound.
Single actually, curvature bridge, but yeah.
So for the pounding effect that you mentioned right now, so the pounding is typically for the bridges that have abutment that are designed to do so. Since these are temporary bridges and as per communication with Caltrans, there is no such a abutment that have the backfall to provide the pounding. And our behavior in 2 abutments is simply a linear behavior because of the soil. There is no shear key to prevent unseating. There is no back wall of the abutment to provide pounding effect or even gap. So that's why the primary nonlinear behavior of such structures are concentrated within the columns.
But then you did consider these calculation both directions?
Yes, it's both directions, yeah.
So the one that you were doing.
So this is for U X and U Y, and the capacity for the yield is the same in transfers and longitudinal.
Nice. And last question, you said that there's no back wall or not a huge one there. Did you check the seat dot if it doesn't unseat?
Yeah, in this stage, it's not checked yet. It's not checked. But it could be checked with the minimum requirement that the Ashdoor SDC provide.
Perfect, very nice work.
Thank you very much.
Thank you for your presentation. I realized you had 4 regions. I was wondering that you did the aggregation for all of those regions and selected specific ground motions for that.
That's correct.
How many you selected for each region for doing the IDA analysis?
So I have not done IDA analysis. It's not linear time history analysis in this. Let me just go through here. Should be on the nexus. Yeah, that is. Okay, so seismic aggregation help us to have a range for the search criteria, the initial search for the ground motion into the peer database. Okay, it provides us the range for rupture distance, magnitude, and shear wave velocity. Not actually shear wave velocity, for the rupture distance and magnitude. And based on that, we had initial list could be 100, 200, 250 ground motions initially selected, then calculate the scale factor, they calculate the MSE, sort them from beginning from the lowest value to the highest value, and select the first 31, which fits within the range of scale factor of 0.323 in accordance to the work by, I think, Baker in 2006. And based on that, these 30 ground motion then rotate twice by 45-degree angle increments, creating 19 ground motion for each case.
Excuse you didn't do IDA analysis.
No, I didn't.
So how do you extract this fragility curve?
So we have 2 different methods. We can use PSDM or we can use IDA to extract the values for the fragility. Here, since it's nonlinear time history analysis, it's not incremental dynamic analysis, we're using PSDM or probabilistic seismic demand model to do the recreation between the engineering demand parameter and also our spectral acceleration.
Oh, I get it. Thank you.
Thank you for your presentation. I have a question on the same slide. So you said that you
Which is
wrote-
right, sorry?
Yeah, the slide.
The
same
slide,
slide.
yeah.
So you said that you rotated your motions like 45 and 90. I was wondering, since you're using your fault motions, why didn't you rotate to fault normal or parallel direction or use the ROD 300 definition of spectral acceleration?
So just since this research is sponsored by Caltrans, many of the details is requested by Caltrans. By using the, not why we don't use the ROD 50 or ROD 100 is because the nature of the work in Caltrans is done by using the geometric mean. That's why we are using right now. And we don't have so many polarized ground motions, only specifically in our location, which is San Francisco, nothing but in Los Angeles. So using the geometric mean is a good approach to combine the ground motions. And again, 245-degree increment is again requested by Caltrans, which is already incorporated in the SDC. Can be used with what you said, but this is the policy that we use in our research.
Thank you. Well, I think there's no more questions. That brings us to the end of today's seminar. A big thank you to Mahdi. Thank you for sharing your research and expertise with us. We want also to thank you, all of you, for attending both in person and online. Your participation and engagement make these seminars a valuable learning experience for everyone. This is just the beginning of the EERI Friday seminar series for the semester. And stay tuned for upcoming sessions with more exciting topics and speakers. With that, I wish you all a great weekend, and we look forward to seeing you at the next EERI seminar. Thank you, and follow us on LinkedIn, please. Thank you. So we'll start this.
Dude, nice job. That was great. Oh, yeah, it was a good job.
Pixel research.
So the purpose of that
UA, I'm sorry
how
for that,
trust
we're
is
sorry
spent
for
its
that,
money
but
building
we're
temporary
research-
justice, right? How do they quantify the cost side? So the question is going to be here because there was an idea at the first that we did, but it was might be needed for designing this which will
Yeah, we are mostly.
can cost them more. Right now, they don't do something for
Yeah.
Because I remember I met you last semester, and then you're also in earthquake. We just kind of scratch the surface to see what's beyond. What is, so nobody's done any assumption.
I remember.
If you did this, you reduce the cost by 10%.
No,
thing is that
last
they're just telling you,
semester, I took
let's use
a seminar
and they're
class,
using it without
doing
experiment.
And then I think I remember you said you're gonna be in the earthquake
Yeah,
engineering.
I'm the earthquake flash, Professor Patel.
Yeah, yeah, yeah.
Oh, good, yeah, I
Yeah.
remember you.